In this chapter, we will cover everything you need to know about lattice energy. In pre-ACE and also in AS level, we already defined how ionic bonding is formed by electrostatic forces of attraction between ions. And also we calculated the enthalpy changes for certain reactions. In this chapter, we will compare the strength of those bondings by calculating the enthalpy changes and also the differences in solubility and thermal decompositions for these ionic compounds. Before any considerations, we need to define what standard conditions are. Standard conditions refer to the temperature and pressure of the reactions. The temperature in standard conditions is to be as 298 kelvins, which is the same as 25 Celsius, and 101 kilopascals, which is the same as 1 atmosphere pressure or 760 millimeters of mercury. The reactions and the equations must be shown showing the state symbols: gas, liquid, or solid. So you are going to put G, L, or S for these states of matter, and also AQ for aqueous solutions. The solutions most likely will have a concentration of 1 mole per decimeter cube if nothing is said otherwise. For an enthalpy change in general, we use the delta H, which is the sign for enthalpy. And if there is a theta in the sign, that means that that is in standard conditions of temperature and pressure. We are going to define lattice energy, and lattice energy is the energy released when 1 mole of an ionic compound is formed from the gaseous ions in standard conditions. In some books, the lattice energy is the energy absorbed by to form 1 mole of ionic compounds from the gaseous ions, and that is something that you need to be aware of, that sometimes in some books the sign of the lattice energy is the opposite. For us, lattice energy is the energy released when 1 mole of ionic compound is formed from the gaseous ions. The solid forms only from gaseous ions. Those are important things that we are going to emphasize. The reactions are always exothermic, and it cannot be measured directly. That's why we are going to use a Boron-Haber cycle or a Hess cycle to perform those measurements or calculations. If you see the values of the sodium chloride or the magnesium chloride, you're going to see that the energy released by the sodium chloride is much less than the one from the magnesium chloride, and that has to be with the ions that are involved. So we are going to see which is the difference between one and the other one. You should stop the video right now and try to resolve these exercises that are going to allow you to see if you understood the concepts that we already covered. Another definition that we need in order to build a Boron-Haber cycle is the enthalpy change of atomization. The representation is delta H AT, and is the enthalpy change when 1 mole of gaseous atoms form from these elements in the natural state. We need to know that if an element is not in the natural state, we need to put it in the gaseous state, and the process is always endothermic. That means that we need to give energy to the substance in order to break those bonds. Be careful with this, because this is a very common mistake. When you have an element like chlorine, which is diatomic, the correct formula would be 1/2 of chlorine gas to form 1 mole of atoms. Remember, that is when 1 mole of gaseous atoms is formed. If I don't put 1/2, I'm going to have 2 moles of chlorine atoms instead of 1. In the case of the enthalpy change of atomization of sodium or in any element at solid at room temperature, we need to break the bonds for the solid in order to get down into a gas. And you can see that both values are endothermic, and they are going to form 1 mole of gaseous atoms all the time. Another definition that we need in order to build the Born-Haber cycle is the first ionization energy. We represent that as delta H IE1 for ionization energy number 1, and is the energy required to remove 1 mole of electrons from those mole of gaseous atoms that we form in the atomization energy to form 1 mole of gaseous ions plus 1. So if we have 1 mole of hydrogen atoms, is not the hydrogen molecule, we are going to form 1 mole of ions of hydrogen, and they are going to release 1 electron. The value is 1312 in this case negative. That means that the reaction is exothermic. In the case of the sodium, when the sodium loses the electron, it requires energy to be given, and the value is 496 kilojoules per mole. The value can be positive or negative depending on the nature of the element. In the case of any element, we can have the second ionization energy, and is represented with the delta H IE2 in this case, ionization energy number 2, and of course is the energy required to remove 1 mole of electrons from 1 mole of gaseous already single charged atoms to produce 1 mole of double charged positive ions. So in this case we have the ion sodium plus, and is going to release 1 electron to form the ion 2 plus gas. And you can see that the second ionization energy of sodium is much bigger than the first ionization energy of sodium, and that is because we are taking out 1 electron from an inner core in the case of the sodium. Electron affinity is the opposite of the ionization energy. It's represented as delta H EA for electron affinity, and is the enthalpy change when 1 mole of electron is added, in this case not taken out, from 1 mole of gaseous atoms to form 1 mole of gaseous ions. Of course, they are going to be negative under standard conditions. In the case of the chlorine atoms, when they gain 1 electron, they are going to form the chloride ions, and the delta H in this case is negative because the chloride ions are more stable than the chlorine atoms. The electron affinity basically defines how easily an electron enters in a gaseous atoms. And when we said that the chlorine gas atoms are less stable than the ions, is because when the chloride ions form, they complete the octet. Most of the first electron affinities are negative, since we are going to talk about nonmetals gaining electrons. Some atoms require more than 1 electron to be stable. In the case of the chlorine, chlorine gains 1 electron and completes the octet, and that is it. So we are not going to have a second electron affinity. In the case of the sulfur, for example, the sulfur has 6 electrons in the last level. So with one only more electron, is going to become sulfur -1, but it's not going to be completed. So we need the second electron affinity, and is the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous -1 ions to form 1 mole of gaseous ions with the -2 charge. Of course, the sulfide -1 is going to get 1 electron to form the sulfide ion, and look at the value is positive because we already have 1 electron extra, and they are going to form like a repulsion, so it's going to be difficult to put the second electron in the same cloud. We are going to see why the differences between the values of the electron affinity between the chlorine and the sulfur in the next slides. We already said that the first electron affinities are all negative values. We are going to analyze the last three halogens, chlorine, bromine, and iodine. We are going to leave fluorine behind. We are going to analyze that separately. From chlorine to iodine down the group, the first electronic affinities become less negative. And fluorine, of course, doesn't follow the trend. We are going to analyze that later. The electron affinity can be analyzed as how much attraction we have between the incoming electron and the nucleus of in that particular element. The stronger the attraction, the more energy is released. So chlorine has more attraction than bromine and than from iodine. That's why the values are more negative. There are three factors that affect the electronic affinity. First is the net nuclear charge. That is the protons in the nucleus minus the electrons in the inner level. So all of them are going to have +7 because they have 7 electrons in the last level. So all of them have 7 more protons in the nucleus than the electrons that they have in total. So that is not going to be one difference. The distance from the nucleus, the more layers of electrons, the more distance, and they are going to have less attraction. So the chlorine is going to have more attraction than the bromine or the iodine ions for the extra electrons, and that's why the values go up. In the case of the shielding effect, this one is the protection from the inner electrons that prevent the attraction from the nucleus, and that happens in iodine. You have more shielding effect that you have in chlorine because you have more layers of electrons. Now, in the case of fluorine, fluorine does not follow the trend because even though the nuclear charge is the same and the distance is very small, the cloud of electrons is so small because it is only the second layer of electrons. So it's already crowded with electrons, so it's very hard to put an extra electron there, and that's why the electron affinity of fluorine is a little bit smaller than the chlorine itself. Let's see what happens when we compare group 6 and group 7. Let's compare first group oxygen and fluorine. Oxygen has a value of -142 and fluorine has a value of -38. The same happens with sulfur. Sulfur has -200 and chlorine has -349. The the group 6 elements have one less proton in the nucleus than the elements in the group 7, that the element that is next to them in the periodic table, and the amount of shielding is the same in both because they have the same amount of layers of electrons. That means that the net pull of the nucleus of the net nuclear charge is less in group 7 than in group 6 than in group 7, I'm sorry, and so they release less energy. So the values are smaller numbers in this case. We said already that the second electronic affinities are required to add an electron in already a negative ion. So in the case of the oxygen, the first electron affinity is 142 negative. That means that it release energy. And the second electronic affinity is super high, 844 positive. The same happens with the sulfur. It's -200 compared with positive 565 kilojoules per mole. That is because adding the second electron into an already negative ion will produce kind of a rejection between the electrons in the cloud, and that's why the values are positive. In the particular case of the oxygen, it occurs more or less like in the fluorine. The atom is so small and the cloud of electrons is so small that it's very hard for us to put an extra electron in a very electron dense space that the oxygen has. When we cover enthalpy in AS level, we use the Hess law for calculating enthalpies that are not possible to be measured. That is the case of the lattice energy, or in this case, the enthalpy of lattice of the compounds. When we have an element in the standard state, we can have several steps to pass them into the ions in the gas state, and then those are going to release energy to form an ionic compound. Passing from the elements in their standard state to the ionic compound directly is going to be what we define as the enthalpy change of formation, and we saw that in the AS level problems. But now we are going to analyze the different steps that we have represented into this delta H1 And knowing that step, we can calculate the lattice energy or the standard enthalpy change of formation, or any of the enthalpy changes that occur when the elements are passed into the gas state. Calculating a Born-Haber cycle is not as simple as a Hess cycle because it requires more steps. So, for example, to calculate the lattice enthalpy of sodium chloride that we have here, okay, we have several steps. We have sodium in the solid state that we need to pass into the gas state first. Then that sodium gas needs to be ionized by releasing an electron that is going to be the first electron, first ionization energy or enthalpy. Then the chlorine atom in the form of molecule needs to be passed into gas atoms. That is going to be the chlorine atomization energy. And then that chlorine gas atoms needs to take one electron to form the chloride ion. That is going to be the first electronic affinity. Based on all that stuff, if we know the sodium chloride formation enthalpy, we can calculate the enthalpy change of lattice, or the lattice energy for the sodium chloride. We are going to do that by using a Born-Haber cycle, which is kind of a graph that looks very similar in all the exercises that you are going to see. The Born-Haber cycle is kind of a Hess law diagram, but with more steps. So every step has an arrow. If the arrow is pointing up, that means that is an endothermic process. If the arrow is pointing down, that means that is exothermic. And we can build up the cycle based on the information that we have. In this case, we have sodium and chlorine, sodium solid and chlorine gas, 1/2, because we need to form only 1 mole of sodium chloride. And the first step is going to be transforming the the chlorine gas into the chlorine atoms. That means the atomization of chlorine. That was a positive value based on the table that you have in the last slide. Once we have the chlorine gas, we have to apply the sodium atomization energy, which is going to be positive 2. That's why the arrow is pointing up. So after the second step, we have the sodium in the gas state and the chlorine in the gas state, and both as atoms. Then we need to apply the first ionization energy of sodium. So the sodium is going to release 1 electron, and that electron is going to form the sodium plus ion. And the next step is going to be this electron that is going to get together with the chlorine to form the chloride ion. Be sure that you change only one thing at the time. In this case, we are going to change first the chlorine, then we are going to change the sodium, then we are going to change again the sodium, and then we are going to change the chlorine into the chloride ions. Once I have the sodium plus and the chloride negative both in the gas state, I can calculate the delta H of the lattice enthalpy for the sodium chloride just by adding and subtracting these arrows that are here. This is kind of a Hess cycle. If I need to calculate the enthalpy change for this cycle, and I need to calculate the, in this case, the lattice enthalpy, I'm going to part from here, and I'm going to part from here and end here by going in the other direction. That's why I'm going to follow the direction of the green arrow. I'm sorry for the the drawing is not very good, but basically you are going to follow the steps here. If again, the same as in the Hess law, if the arrow is in the same direction as the process, we are going to leave those signs as they are, or if they are in the opposite direction, we are going to change the sign. So in the case of the first electronic affinity of the chlorine, you can see that there is a negative sign here because the arrow points on the top, but the value is pointing down. So that is going to be giving me the negative sign. Let's analyze again the sodium chloride Born-Haber cycle. The first thing is going to be sublimating the sodium that we have as a solid. So in this case, we're going to have the sodium plus the chlorine molecule, half the chlorine molecule, to form sodium gas plus the chlorine, half the chlorine molecule. The second is going to be the enthalpy of atomization of chlorine. In this case, we are going to have, as a result, both as gas atoms. The third one in this case is the ionization energy of sodium. In the ionization energy of sodium, we are going to obtain sodium plus, that is going to release one electron, and the chlorine gas is going to stay like that. That chlorine gas atom will absorb that electron, will be attached to that electron by the electron affinity of chlorine, forming the chloride ion. And as a result, we're going to have the sodium plus ion and the chloride negative, or the chloride ion. By calculating the sodium chloride enthalpy change, the lattice enthalpy change of sodium chloride, we are going to obtain the sodium chloride ion. But also we can calculate the enthalpy change of formation of sodium chloride. That is going to be pointing down, if you see, because the enthalpy change for the lattice enthalpy of sodium chloride is very large. In this exercise, you are going to calculate the lattice enthalpy for magnesium chloride. The values for the atomization energies, the first ionization energies, and the electron affinities can be found in your book. So you should stop the video right now and try to resolve this exercise. In this second exercise, you need to calculate the enthalpy change for the reaction that is on the screen, and you have the values that you should use or need for your calculation in the table below. So stop the video and try to resolve it. These are just some lattice enthalpy values, so you can compare your results with the values that are in this table. Most of these values are found in books or even the internet.